Hello everybody and welcome to another Jakarta Tech Talk. Today's presentation is on managing state in elastic microservices, and we are lucky enough to have Alex Sayevich, Coherence Architect at Oracle. If you have any questions throughout this presentation, please feel free to just ask them in the chat bar on the right side of your screen or at the Ask a Question button on the bottom bar. I won't take any more of your time, and I will turn it over to Alex. Thank you.
Thank you for the introduction, and thank you everyone for joining. As some of you know, back in June, we have released two things. We have released Helidon 2.0, which is the next major version of Helidon microservices framework. And we have also released and announced the Coherence Community Edition, which is an open source edition of Oracle Coherence and in-memory data grid, which has been around for almost 20 years now. As part of that effort, we have also built an application that is used to demonstrate how the two integrate and how they work together and how they make building stateful microservices easier while still allowing them to scale pretty much as you need to. So first I'll introduce the application that we built. We didn't actually build the original application. I took the existing microservices demo application that was created by WeWorks back in 2016, I believe, and was published as an example of how you would build modern polyglot microservices applications. It was kind of intended to serve the same purpose that Java EE Pet Store served back in the day, to demonstrate how you would build enterprise application using Java EE technologies. So we started with that, and the architecture of that application, it looks something like this. So it has a number of independent services. They're all packaged into Docker images, and then the original demo had a number of different ways to run it, because back then Kubernetes was not de facto standard for running these types of applications. But basically it had one front-end service, which was, and then a number of back-end services, the service to manage shopping carts, to manage orders, users, product catalog, and then also to process payments and to create shipments. So the original implementation of that application used Node and Express to implement the front end. And then for the backend services, it was a combination of Spring Boot running on Java, obviously, and Go microservices. And then for backends, they use combination of MongoDB and MySQL and RabbitMQ. And then the front end also had the option of using Redis for session state management. So let's take a look. I actually have the original demo running here, and I'm already logged in. So basically the application, when you run it, looks something like this. You can look at the home page, you can go and browse product catalog, you can search for items in the catalog, add something to cart, and then you can look at the cart and check out. So when you check out, the order gets created, and that's pretty much it. So you can view the order and see what you ordered. So it's your typical e-commerce application, right? I mean, it's a good example to kind of show how all of these services work together. But it does have some underlying issues that are kind of hard to avoid unless you change the architecture a bit. So the problem with this is, are these services scalable, right? And when I say are they scalable, it's not enough to scale. Obviously, we have stateless Spring Boot services, we have stateless Go services. It's easy to scale those. It's you can simply tell Kubernetes to add more pods, and it's all good. But you also need to be able to scale the backends, right? You need to scale MongoDB, you need to scale MySQL, you need to scale RabbitMQ. Those things are typically not as easy. I mean, they're managing state, they're stateful, so they're not as easy to scale with or without Kubernetes, right? I mean, there are ways to do it there, but it's a project. I mean, you have to set things up. You have to set up their clustering support. Usually there is an operator involved that you need to configure, and sometimes those operators, even for open source products, are commercial offerings and part of only enterprise editions, et cetera, et cetera. So while it's possible, it's definitely not trivial. The second question is, are those things highly available? Well, until you scale them, they're not, right? Because if we have just a single data store, if that data store goes down, your application is down, right? And then the last question is how easy it is to monitor each of these services. And again, this is where the complexity of the architecture comes into the picture, because the more moving components you have, there are more things to monitor, there are more things to manage, there are more things to scale, et cetera, et cetera. So, and then you're dealing with different platforms, which is fine. I mean, polyglot microservices are perfectly acceptable, but you better have a good reason for it, because each platform will require different way of monitoring and management, and you have to embed things like open tracing and metrics, et cetera, using whatever libraries, whatever features the application, the platform you're building on provides. So looking at this application, let's see why this is an issue. So this is what we end up, when this application is deployed, this is what we end up having on the back end. And I'll show you the pods that are running, and then I'll show you what is backing those pods. So you can see that, based on the pod names, you can pretty much see that all of these are backed by the deployment set. And we can show that really quickly. And you can see that there are separate deployments, what I mentioned earlier. There are separate deployments for the service itself. For example, card service, that's our Spring Boot stateless front end, but then there is also corresponding database deployment. And again, for a simple demo, just to showing that this works, this is fine, but you would never actually run this database this way. You would never run it as a Kubernetes deployment, because it's ephemeral, essentially. If this pod goes down, you lost all your data. And you also, you can scale this. I can do kubectl scale cards deployment to as many nodes as I want, but I can't really do something similar with CardsDB, because in order to scale this, which in this case MongoDB instance, I need to configure Mongo for scalability. I need to tell Mongo how to discover other nodes. There is all kinds of additional configuration that need to happen. So none of this. Catalog is backed by MySQL, same thing. I mean, it's not a trivial thing to scale. You need to configure masters and replicas, et cetera, et cetera. Same thing would be with Redis, right? You need to configure Sentinels, you need to configure Redis cluster, you need to configure where master copy of the data goes, and then configure one or more replicas for each, et cetera, et cetera. So that's the problem, and that's the problem because we are pretending that a stateful system is stateless, and it's not. I mean, it simply isn't. I mean, if your service depends on data store, it cannot be stateless. I mean, if it cannot handle the load, and we know this, like we all, well, maybe not all, but many of us who are old enough remember from the early Java EE days when we started writing Java EE EJB-based applications, and everything runs smooth as long as you have a single node, because that node is able to cache a lot. It knows it's the only node in the cluster. There is nobody else talking to the database. There is no reason to synchronize data. So early Java EE servers were able to cache a lot as long as they're in a single server mode. But you add a couple extra nodes, and all of a sudden that caching gets turned off and your database load increases. So how far can you increase the load without your data store falling over, right? If you cannot handle the load created by 10 stateless instances, does it matter if you can have thousands of them? It doesn't. I mean, you're just going to make things worse. You're going to reduce performance. You're going to eventually make your data store kill over, and your application will be completely unresponsive. Similarly, if your data store is down, are your stateless services able to process requests? They're not. I mean, they depend, the pattern that we see in many of these services that we consider stateless is the request hits the API endpoint, and then the implementation within that endpoint talks to some kind of data store, gets the data from data store, processes data, stores the data in the data store, et cetera, et cetera. So what we did as part of Helidon and Coherence launch, we took this application and have rewritten it to use slightly different architecture. So we left the front end as is because we wanted to show that the original front end can still works with the new application, with the new backend services. But we have rewritten all backend services to use Helidon microprofile and to use Coherence as an embedded data store. And this is major difference in the picture, right? Coherence is not something that's outside now; it's actually embedded into the application. That changes architecture quite a bit. So, for those of you who are not familiar with either Helidon or Coherence, I'll just do a quick overview. I mean, this talk is not about, well, it is and it isn't. I mean, it's not necessarily about low-level details about either technology, but it is about how you can use them to build applications in an easier fashion than most people do these days. So Helidon is a microprofile 3.2 implementation. It has two different editions, Helidon SC and Helidon MP. I'm focusing particularly on Helidon microprofile edition in this case, and that's what the sample application uses. So it implements microprofile 3.2. It also supports a bunch of Jakarta E components that we need, and that microprofile needs things like CDI and JAX-RS, etc., JPA. And then it also has some additions that some of the other implementations don't, and those are kind of important. We do use them for communication between order service and payment and shipping service in the application. So one thing that Helidon adds is support for gRPC. So you can write not only REST services, but you can also write gRPC services, which is, I'm hoping we can standardize this someday, but at the moment it's not part of the microprofile, and it's basically Helidon proprietary extension in order to support gRPC microservices. And then Coherence at a high level, you can really think of it as a distributed persistent KV data store. It's kind of similar to MongoDB or Redis. It can be used for the exact same types of applications, but it is much easier to scale out. I mean, there is major difference between some of these technologies. While the features are the same, Coherence was designed from the get-go, from the very early days, to be a distributed technology. While Mongo and Redis, for example, they were designed as a single process servers, and then they were kind of extended. It was a bolt-on to allow them to be clustered and to allow them to support HA and scale out environments. So there, this can be seen once we see how easy it is to scale Coherence. It becomes obvious that one thing was designed for scale out and the other one isn't. If you ever try to scale Mongo or Redis. It is elastic, scalable, and highly available. It partitions data across cluster members, regardless of how big the cluster is, and ensures there is backup copy for each data entry. And what's important in this refactoring, it is embeddable into any Java application. Coherence is effectively a library. We do have a server that you can run as a standalone thing, and you can use different APIs and write clients that talk to that server and store data and get and read data, et cetera, et cetera. But for most applications, and in this particular example application, Coherence is really just a library that can be embedded. But while it's embedded in every single process, it actually allows all those processes to cluster together and to talk to each other and to basically partition data across them. So the larger you make the cluster, the more capacity it has, the more both for processing at the application, at the API layer, and for data storage. And it just becomes one big system where every member is aware of one another and aware of all the data that's stored within it. It is as easy to use as Java util map, at least for basic functionality. Coherence named map interface, which is our core interface when you're dealing with for dealing with a data store. actually extends Java util map and provides, the extensions that we provide are very useful to implement some of the distributed computing constructs. The ability to send us processing into the cluster and to process data in place, to aggregate data in parallel across the cluster, to execute queries against the map, et cetera, et cetera. So those are the types of extensions. But for basic operations, as you'll see in some of the code examples later, it really is, you can do map get or named map get and put and compute, et cetera, et cetera. So we'll see some of the examples later. And as I mentioned in the opening, as of June, Coherence is free and open source. Well, Community Edition is, and I do want to point out that unlike some of our competitors in the in-memory data grid space in particular, and even some of the competitors in the larger data store space, we don't really. What we try to do with the Community Edition, I mean, Coherence has been around for almost 20 years. It has been around since 2001, and it has powered mission-critical systems across the planet for almost 20 years. But when we decided to release Community Edition, we did not want to put carrot on a stick out. We wanted to release something that can be truly usable on its own. The features that we left out, the features that are commercial only, are related to federation and hot cache, which is replication from a database. They're kind of advanced features, but what we give you out of the box, both from development perspective, from what you can actually do in production, and from the management monitoring perspective, all of those things are free and part of Community Edition. The operator is completely free. The monitoring extensions that I'll show in a minute for Grafana and Prometheus are basically out in the open source and free as well. So you can do a lot. Everything I did in this application, it uses nothing but the Community Edition, and it provides enough features for most applications. And then I want to talk about how Coherence and Helidon MP fit together. So, once we learned about microprofile and started seeing that microprofile is gaining traction, we wanted to integrate with it. And I'm using Helidon in this example, but Helidon microprofile integration is really a microprofile, Eclipse microprofile integration. So we use standard microprofile APIs. We just happen for this demo to use Helidon as a backend, and because we need gRPC services, we need to use Helidon because that's something that's specific to Helidon, and no other microprofile implementations have it. But for the most part, everything that's on this slide would work with any microprofile, or should work with any microprofile implementation. I'm not sure. We haven't really tested it with every implementation, but it should. The integration is in these four boxes that are kind of highlighted in the lower right corner. So I'll start with CDI because it's kind of the cornerstone component of it. So we use CDI to bootstrap Coherence. Again, Coherence is just a library. It has an API that allows you to start a server, a Coherence cluster member inside of any Java process. So we use CDI extension that Helidon bootstraps basically, and starts a Coherence storage node, starts a Coherence cache server. We also use CDI support to allow injection of Coherence resources, such as named map, into JAX-RS services and gRPC services. We can use it to handle server-side and client-side events Coherence provides, which I'll show in a bit. And then we use it to inject CDI-managed objects into Coherence itself for different things. We also integrate with microprofile metrics. So Coherence has a fairly extensive set of metrics that are internally managed as using JMX. But we did implement a couple of years ago, we implemented support for metrics, registries for metrics adapters, basically. And we have written, as part of this effort, we have written a microprofile metrics adapter that allows us to publish all of those JMX managed metrics into any microprofile metrics registry. So they get exposed to the same /metrics endpoint with all the other application and application server metrics. We've also implemented integration with microprofile configuration. So you can use microprofile config to configure Coherence itself. There are a number of options that Coherence allows you to specify either as Java typically as Java system properties or in a Coherence specific config files, but now you can use any microprofile config source to provide those things. So the same system properties that you were always able to provide, you can now also provide with using environment variables or Helidon's application YAML or microprofile config properties or any other mechanism that your MP deployment supports. And then finally, we've added support for open tracing, which allows us to see the request all the way from the API endpoint down into the data store, down into the guts of the data store, across members, across cluster, et cetera, et cetera. And we'll see that in a minute. So let's look at how this application works. So again, we're using the same front end, so there shouldn't be any difference. You may see that the order IDs will become a little bit shorter because in our new implementations, we've shortened them a bit. But apart from that, there should be no difference in functionality. So you can obviously browse the catalog. You can search. You can add products to cart and check out. And again, as I said, the order number is a little bit shorter, and you can still go in and view the orders. So that's pretty much it. Functionally, the application is exactly the same, but the front end is exactly the same. I'm using actually the same Docker image for the front end container that the original application uses, but the back end is completely different. And to see how different it is, and let's see what we actually have here. So if I look at a list of pods running Kubernetes for the Coherence application, you will see that there is basically only one pod per service. So there is cart 0, catalog 0, order 0. There is front end, which still uses the original deployment, as you can see from the mangled GUI at the end. But all of the backend services have 0 behind them, and there is only a single one of them. There is no separate DB. There is no, and the reason why this is the case is that all of these are backed by stateful sets. So each one of them can have the persistent volume attached, and it can store data on that volume. You can see if I list stateful sets that I have 6 of them, and there is one pod in each one. And because we have Coherence operator running here, we can also list Coherence deployments, which are what creates those stateful sets. And when you do that, you can actually see a bit more. You can see that cart's deployment belongs to a sock shop cluster. We've chose to run all of them in the same cluster as different roles. We could have easily set them up to run as completely separate clusters, but this makes some of the monitoring features I'm going to show you in a minute a little bit easier to demonstrate. So we have different roles. We have role per service, and we have one replica and one ready replica for each of those Coherence deployments. Now, how is this better, right? Well, you haven't seen it yet, but these services are stateful. They don't need separate data store. And as you'll see in a second, they are as easy to scale as the stateless one. They're as easy to scale as the Spring Boot or Go stateless services from the original application. High availability is built into the architecture. Again, not when you run with single pod per service, but it will be in a second. Support for monitoring is built in, and it's also extensible. And the implementation is significantly simpler. So let's look at some of those things. So I'll start with looking at the monitoring. So this is Grafana dashboard that you get effectively out of the box that allows you to see what's going on in a Coherence cluster. So this is our main dashboard. So you can see that we have 6 cluster members, 1 for each service. But you can also see here in red that we have 12 endangered services. And total cluster heap is at the moment 19 gigabytes or so. So we have 6 members running. Each one of them, I believe, is set to 3 gigabytes, three something. So that's about right. So, and then you can see some additional information, but on this dashboard we can focus on this. And then we can also look at services dashboard, and we can see that HA status for each service at the moment is endangered. So we have cart service, catalog service, order service, etc., etc. These are not our microservices. These are at the storage level coherent services that are used to store the data for each one of them. So how do we fix that? And then we'll before we fix it, actually, let's look at this. I've created some orders earlier, and I created one just now. So you can see here that we have different caches, one on each service. We have users. We have 5 users at the moment consuming 4.5 kilobytes. We have 6 shipments for 6 orders and 6 payments for 6 orders. So those things match, and they should match going forward. And then we have catalog service with only nine products in a catalog, but that's good enough for what we need here. So this shows you basically how much data you have in the cluster, how much data you have in each individual cache, both how many objects and how much memory they're consuming. It also shows you the indexes that you have, and in this case, only payment service has an index, which is consuming kilobyte, etc., etc. So because we are running with a single member per service, we're obviously in danger. We don't have data backed up anywhere, etc., etc. So let's fix that first. And the way to fix it is to scale this application out. And to do that, I'm basically just going to run for each of the services. I'm going to run the loop and do and execute this command. So I'll scale Coherence deployment with the given name to 3 replicas. And this will take a minute. We'll see that Kubernetes should scale each of these services. And if we look at set of pods, we'll see that the new pods for each service, we'll see that in addition to pod 0, we should see pod 1 and 2, and they should be in some stage of starting. Okay, so if we look at Coherence deployments, we should see that now we have 3 replicas for each. Only 1 is ready. If we look at the pods, we'll see that they're starting up, and in a minute or so, they should all be started. And while we are waiting for that, let's go back here. So you can see that for some services, now we see that there are 3 members, and now all the services are, well, almost all the services. The services are converting from 1 to 3 members, and they're marking their status HA site safe. And what site safe means, I mean, Coherence has different levels of safety. You can be endangered, which is what we were initially. Then you can go from endangered to node safe, which means there is another JVM on the same machine that is storing a backup copy of the data. And then you can go to machine safe, which is, there is another JVM on a different machine that is storing backup copy of the data. And the site safe is kind of the highest level. There is rack safe in between, with backup and primary data being on different racks. Site safe is kind of the highest level of safety, and it means that the backups are actually stored in a different data center. In this case, in a different availability domain within the OK cluster, the Kubernetes cluster I'm running on OCI. So, because and all of this happens automatically. There was nothing I had to configure to make Coherence create backups as far away from as far away as possible. I mean, it basically is aware of network topology and where each node is running. It gets configured automatically by Kubernetes operator using Kubernetes metadata about which availability domain each member is running in. And then it ensures that if I have multiple availability domain, when it creates backups for the data, it creates them as far away as possible. So if we look at cache's summary, nothing has changed, right? We've added a bunch of nodes, the data got rebalanced across different data centers, but we still have 6 orders and payments and shipments, 9 products, etc. And if we look at the main dashboard, which doesn't seem to have okay, so now it refreshed. So we have 18 cluster members, we have 0 endangered services, we have now 58 gigabytes of heap to store the data in, and we obviously have 18 application servers that can process our REST and gRPC requests, right? So that's really what this means. I mean, we were able to scale the services as easy as the stateless ones by simply doing kubectl scale. High availability is built in. If any of those pods goes down, if a whole data center goes down, in this case, if a whole availability domain goes down, so we are not going to lose any data because all of our data is site safe. Monitoring is built in. I've shown one component of monitoring, which is our Grafana dashboards. I'll show another one, which is tracing support, in a minute. And then we'll look at the implementation. So before we do that, scaling to 3 nodes is fun and everything, right? But that's not what real scale-out architectures are all about. So God willing, because somebody seems to be using my Kubernetes cluster, but I'll give it a try anyway. Let's change this and let's really scale this thing out. So let's scale to 50 nodes per service. And this will take a bit. I mean, it takes time for Kubernetes to spin all these pods, but when it's all said and done, we should end up with a 300 node cluster storing almost terabyte of data, or with a capacity of about terabyte on heap, and spread across 6 Kubernetes nodes that I have. So this will take a minute, but if we look at it here, you can see that there is something happening and the activity is increasing, but we'll come back to that in a second. In the meantime, we can look at some of the tracing functionality. As I mentioned earlier, the tracing is built into the whole thing, right? Because Helidon supports tracing, Coherence supports tracing. We can actually embed Coherence spans into traces created by Helidon. So in this case, we see that there was HTTP request coming in as a HTTP post to the orders endpoint, and that order service then did a couple things. It executed this JAX-RS method, orders API new order, which then called out to a couple other services. It called to the cart service to get shopping cart details, and then it called to the user service multiple times to get address for the user and to get credit card information and to get the actual customer information as well. And then finally, it called into Coherence. So you can see that in this case, this is just the CDI being event-driven order processor. Process order method was called, which called save order method on the Coherence order repository, and then ended up in Coherence. So this is where effectively Helidon application stops and Coherence begins. So now we are looking at traces in Coherence itself. So you can see that we submitted put request on member 5, and that request was processed, because in this case, this was done when I only had single member for each service. This request was also processed by member 5 and on partition 147. on this particular worker thread. So again, this is just a simple example that shows how you get tracing information throughout the stack, all the way from the API endpoint down into the data store itself. And then we have some other traces that we can look at. For example, this is aggregate request that I executed again when I had a single node. So request was executed on this node, and it came from the HTTP request to catalog endpoint. So I wanted to get number of items in the catalog to show on the UI. And that executed aggregation request. It called into getSockCount method, which called Coherence catalog repository, which executed aggregation request against the data store. And you can see that there is only a single member that processed. Now, if I do that same thing now, while this thing is scaling out, I'm not sure how many will have, but okay, so that should be enough. I just need to refresh this, but we should see significantly more aggregate process requests, because there should be as many of them as there are members, because aggregation is one functionality that actually scales out and executes in parallel across the cluster. So if we look at the latest one, you will see that unlike 11 spans that we had before, we now have 203 spans, because the cluster is still scaling. And you can see here that we basically have many. Oh, this is different, but this is the aggregate request. So the aggregate request is sent to a bunch of nodes and executed in parallel. You can see from the trace here. I mean, it doesn't really change the aggregation. Obviously, everything is running a little bit slower because the system is in a state of flux. It's scaling up at the moment, so it's not fully stable. I mean, there is additional load on it that normally wouldn't be there. But you can see that these requests are basically happening across number of nodes in parallel, as many as we have at the moment. So going back to this, let's see where we are. So we'll see that card service already scaled out to 50 nodes, 50 members. Order service scaled out to 50. The other 4 are still in progress. So let's go back to the deck and look at some of the implementation details. So the implementation for this whole thing, and actually, for the whole example, is on GitHub. It's available. Everybody can use it. If you go to github.com, helidon-sockshop/sockshop, that's the main repo where Kubernetes deployments file and root of the documentation is, and then you can drill deeper into individual services. There is also update this shell script here, which is documented a little bit further below, that allows you to check out all the other repositories locally and allow you to build them using Maven and everything. And if you go through documentation, you'll be able to both run this locally and also build the Docker images that you can deploy into your own Kubernetes cluster, or you can use the ones. I mean, the ones that we built as part of the CI process are actually deployed to Docker Hub, so you can just use those. You don't need to build it necessarily in order to run it in your own Kubernetes cluster. You can just run the Kubernetes script. So you can go there and get the documentation. And I do want to point out, while the focus of this talk is on how Coherence makes things simpler and how allows you to manage state in a scalable way and build these elastic microservices, the actual implementation on GitHub has multiple backends. So Coherence is only one of them. There is also Mongo backend. There is Redis backend, which is somewhat not quite what it should be, because it oversimplifies some things, and it works with a small data set we have in this particular application, but it wouldn't work for anything larger. And there is also a MySQL JPA-based implementation. So you can take a look at any of them. We hope you're going to choose Coherence for the reasons that I just described, but the application is a good example of how you would build these types of applications using any of those backends. So let's look at some of the things that make it easier when you're using Coherence. So there is no impedance mismatch, first of all. I mean, JPA tends to complicate things quite a bit because you need to go from object to relational world. Coherence just stores Java objects. Obviously, it serializes them, and there are a couple different serialization mechanisms that are supported, including basic Java serialization, but they're a lot more efficient. There is also JSON serialization that's supported, and there is a portable object format, which is what most of our users typically use because it's most efficient and most compact format, so it allows you to store more data in a cluster of a given size. The other thing that's important is Coherence allows you to store rich domain models. We can actually perform operations on your rich domain objects inside of the cluster using, in this case, in-place processing. So in the code sample at the bottom, you see that we use CDI integration to inject Coherence named map into this JAX-RS resource, and then add item is, well, you can't really see it's JAX-RS resource, but trust me, it is. When the add item method is called as part of the post request, we basically do what you would do with a map. We send a lambda to compute method for a given cart ID, and we call cart add item, which internally has all the logic necessary to add item. For example, if the item is already in the cart, it will simply increment the quantity instead of adding a completely new item, etc. Otherwise, it will add the item, and then it returns the new cart, the updated cart. So while this looks like what you would do with a regular map, there is actually a very subtle but very important difference here. This lambda that is highlighted, that is sent to the compute method, will actually execute somewhere in the cluster. We don't know where, and we don't care where. It will execute wherever the cart with this given cart ID exists. It will be sent to the cluster. It will be executed on the storage node that owns this particular shopping cart, and then the result will be returned to this member, which will then return it to the front end, and front end will display updated cart. So it's a very subtle but very, very important difference. It's one of those distributed computing extensions that I mentioned earlier. It's much more efficient to send processing to the storage node that owns a piece of data and update data in place than to what we would typically see in applications that use conventional data storage. You would have some kind of read from a data store to get a shopping cart. You would update it locally on this particular application server where this API endpoint was hit, and then you would write it back. I mean, that works, but it's not very efficient. It's just you're sending a lot more data than you need to over the wire twice. You're doing processing, so putting additional load in your application servers, et cetera, et cetera. So this allows you to do things in a much more efficient manner. Then another thing that we used in the example that I would like to highlight is that the support for rich event model that Coherence provides. Everything in Coherence is reactive internally. There are events for many things. Like there are events, in this case, I'm listening for event on a given map, which are probably one of the most useful event types. You want to listen when things in the map change. So I'm listening, I created on order change, and I use basically CDI async observer on map orders for inserted and updated events. And whenever an entry is inserted or updated into these order maps, I will receive an entry event. And from that entry event, I can get the value. From the value, I can get the status of the order. So in this case, if the status is the order was created, then I can submit it for payment processing, and basically be done with it. And then in the next iteration, once the payment is processed, then it will see that state was changed to paid, and it will call the shipping service to ship the order. So this is just an example of how you can easily write event-driven applications using Coherence, and especially Coherence CDI event support. And then something that's not really Coherence specific, but I did mention earlier, something that makes Helidon somewhat unique in the microprofile implementation space. Helidon has built-in support for a gRPC server, and it was pretty much designed based on, kind of inspired by JAX-RS, obviously with the gRPC slant. So you can mark a class. You can still do things the way you would normally do with gRPC. You can start with a proto file. You can build your stubs. You can implement them, and we'll happily run service implemented the conventional gRPC way for you. But we do provide a much easier way, much easier framework for building gRPC services. You can basically start with a class just like a JAX-RS resource. You can mark it with a gRPC, which says that that this is a gRPC service. You can specify marshaller to use here. While you can easily, by default we still use protobuf, you can easily specify different marshaller. In this case, because we already had support for JSON because of our REST APIs, we decided to use the same JSON serialization for gRPC services instead of re-implementing them using protobuf. We could have used POF as well because we, at least in the Coherence implementation. And then you annotate, just like in JAX-RS, you annotate individual endpoint methods with, where you would use get and put and post to annotate REST methods. In JAX-RS, you use gRPC equivalents, kind of that. You specify a method type. You specify whether something is unary method or server streaming method or bidirectional method or client streaming, et cetera, et cetera. And then you simply provide the implementation for it. And there is a lot that goes under the hood here. If you've ever done gRPC, you know the gRPC expect gRPC methods take stream observer as the second argument, and then they call on next, on complete, on error on those stream observers. All of that still happens under the hood. We're still using standard gRPC Java implementation for everything, but this allows you not to have to worry about that. We'll take whatever you return and we'll either stream it back. If you mark this method as server streaming and you return collection of authorizations, we would stream that collection back. You could also return a stream of authorization, then we would stream it back. Because it's marked as unary, we will basically send the whole collection as a single response. We'll serialize it and send it back. You can still use all of the microprofile metrics annotations. So in the second example, authorized method is metered, so we can see the metrics for it, and et cetera, et cetera. So that's your server side. So implementation is simple. Oh yeah, and another thing, if we wanted to make this implementation asynchronous, all we would have to do is change the return type from authorization, for example, in the second case, from authorization to completion stage of authorization, and that would effectively make it async. The implementation itself obviously needs to return the right thing, but that's what you have to do from a development perspective. So that's on the server, and then on the client, it's very similar to what microprofile REST client does, right? So you define the interface for the client, you specify the method that you want to call, and it can be a subset of the methods that are exposed on the server. In this case, we only care about authorized method. We don't care about the one that gives us all authorizations for the order. And you specify which server-side gRPC you want to call. In this case, it's payment gRPC that we defined earlier. Specify the same marshaller, specify the channel, which is configured. It's basically a combination of host and port that you want to connect to, and it can be configured using microprofile config, like many other things. And then at the usage side, you simply inject gRPC proxy for a payment client, and we'll create a proxy. We'll make sure that we call the right methods and that we convert responses into the right responses. And again, if we change this return type to completion stage of payment, then we would get a payment. And notice that we're not using the same types, right? We're using payment here we've used authorization here because these are different services. They don't share anything. They don't share the types. I mean, these types are compatible at the serialization level. They're JSON compatible effectively because we're using JSON for serialization, but they're not actually the same class. They're not the same type, and because they really shouldn't be shared in a proper microservices application. So let's see where we are with this. I'm hoping this should be done by now. We're pretty close last time. Yeah, so we have 50 members in each. And if we look at the dashboard, oh, not that one is irrelevant. So you can see here on the services dashboard, we have 50 members for each service. They're still site safe. I mean, nothing's changed. Once we went past 3 members, because we only have 3 availability domains, so we were site safe with three members per service, but now we have 50 members per service. What is interesting, I mean, we still have the same data as it should be. I mean, we haven't lost anything in the process. And then if we look at the main dashboard, we now have 300 cluster members. We have almost a terabyte of heap in the cluster, and we are using about 2 gigabytes. So that basically shows you, again, scaling was as simple as doing kubectl scale with the number of replicas that we want. And the difference is we have now 50 pods for each service. And to make it more obvious, let's do this. You can see that we have a bunch of pods for each service, and they all are they're all behind Kubernetes services that allow them to both process API requests that come to Helidon, whether they're REST or gRPC, or to store the data. So they're basically used for both. And you have quite a bit of capacity. We could scale this more. We could make JVMs larger. We could start more cluster members, but unfortunately, this is about as much as I can do given the Kubernetes cluster that I have at my disposal. But I think that's pretty much all I wanted to show. So to learn more, you can go, to learn more about Helidon, you can go to Helidon.io. There is also Helidon blog on Medium, where there are a number of useful articles. And then for the source code itself, obviously, everything is on GitHub under github.com/Oracle Helidon. And there is Helidon Slack channel if you want to ask questions ask Helidon developers how to do something. If you run into issues, that's probably the best place to start. And similarly for Coherence, if you go to coherence.community, that's where Coherence Community Edition is hosted. Obviously, there are commercial Coherence editions that are on OTN, and you can download them from there if you need some of the advanced features that are not available in Community Edition. There is Coherence blog on Medium as well, where Harvey and I published kind of introductory article on Coherence, which is a useful read if you want to learn more about how it works and why it works the way it does and what you can do with it. There is also an article that was recently published in Java Magazine that shows a different sample application, but kind of explains the reasoning behind it. It's kind of similar to what I described here. You can get Coherence source code on GitHub as well under Oracle/Coherence. You can watch a number of videos both for older and new Coherence releases on our YouTube channel. And then just like with Helidon, if you have any questions, if you need help, assistance, and you want to talk directly to us, you can join Oracle Coherence Slack channel. So with that, I think I'm pretty much done. And we haven't had any questions as we went along, so I'll open for questions if anybody has any.
Yeah, if anyone has questions, please feel free to ask them in either the chat bar on the right-hand side of the page or in the Ask a Question box at the bottom. Thank you, everyone, for joining today, and thank you, Alex. This entire talk will be available both at the link that you guys used to get into this crowdcast as well as on YouTube at the Jakarta EE page by end of day today. So far we have no questions, so I'll give it another minute, but then we will wrap it up. All right, so I think we are good here today. Thank you again, Alex, and thank you everyone for joining. Enjoy the rest of your day.
Thanks. Bye.